Okay. So, sorry. So in this lab, in this semester, in this heat power lab, we are supposed to cover 6 experiments. Okay. So normally you would be doing the experiments in the class. Doing the experiments in the class means these experiments. I mean, it's not something you normally you do yourself by hand, because some of the experiments are a bit complicated and some of the experiments are a bit big. I mean, not in this semester, but in the other semester, there is another semester where you will be doing where the experiments will be a bit bigger and more complicated, and it's difficult for one single individual to do it. So generally, what is done, and more importantly, what is very crucial, what becomes very crucial here is that in heat transfer experiments, it takes a long time to for the setup to reach a steady state. Okay, so if you start the experiment all by yourself within the within the class hour, then it becomes very difficult to to complete the experiment within the scheduled time of 2 hours. I mean, not in all experiments, but in most of the experiments. So that's why even in the physical class, what is done, the the setup is switched on long before the start of the class, so that by the time the class starts, it reaches a steady state and you can take the readings. Okay. So that way, apart from actually seeing the things being operated, you are not missing that much in this particular set of experiments, because I will try to explain the I'll try to explain the setup uh, in full details, and you will be also and then I will also provide you with some data. Okay. uh, so basically, in heat power laboratory, have you done any other laboratory in the mechanical department? Possibly not, right?
No, sir.
You have 2 more labs in this semester only.
Yes, sir.
The fluid
Fluid lab.
the
Fluid and
fluid
applied mechanics.
Yes,
mechanics
sir.
lab. Yeah, so you have 3 labs in this semester. So in that way, I mean, this will more or less be the pattern in all the mechanical engineering labs. I mean, which is unlike the physics lab or electrical engineering lab, where you actually work out with the with the setups, make the circuits and everything, and run it all by yourself. So unlike that, here normally you do not do all the experiments by yourselves. So here in the heat power lab, there will be two semesters of labs. One is this semester, fourth, second year, second semester. That is your fourth semester. You will again come back to the heat power lab in the probably in the seventh semester. That is fourth year, first semester. So here the focus will be mostly on heat transfer experiments. I mean, this lab is called the thermodynamics and heat transfer lab. Although right now all the 6 experiments that are covered are all of heat transfer. There is they are not directly, they are not related to the thermodynamics directly, but there are 1 or 2 thermodynamics based experiments also. But in the fourth year, the lab, when you come back to the lab, they will be mostly related to the different thermal engineering devices, like an air conditioning system, a refrigeration system, a mini power plant, mini steam power plant, an performance test of an IC engine. Actually, there is a real Fiat engine which will be run, and you will test its performance. So these things require. I mean, those experiments are kept in the fourth year because they will require. I mean, they will be done after you have covered the thermal engineering devices like IC engines or steam power plant or refrigeration and air conditioning. Okay, but in this semester, the experiments that you will be doing, they will mostly be applications of or demonstrations of what you learned in heat transfer course. But in the measurement for the measurement part, especially in experiments where convective heat transfer is involved, forced convection is involved. There you have to measure the flow rate, the flow velocity. So for that, many of the measurement devices that you studied in fluid mechanics, like U tube manometer or inclined tube manometer or orifice meter, these kind of things you will have to study. I mean, these things will also be used. So what you learned in the fluid mechanics course, that will also be useful here. Okay, and the format here will be what is normally done. I mean, I'll try to stick to the normal protocol as far as possible till we are able to begin the physical classes. I hope sometime in the session we will be able to start it. I mean, after that, if time permits, if there is enough time, because there are only six experiments, if time permits, we can repeat the experiments at least for a demonstration purpose. But right now, let us stick to the online mode and do it, because what you will be doing, that is pretty much same whether whether you actually come to the lab or and do the experiment, or you do not, because the thing that you will be doing, basically you have to get some data and prepare some report. Based on that, you have to prepare some report. So the only difference is that in normal cases, the data will be collected by you only in the during the lab hours. But here, I will probably provide you some old set of data. Okay.
Okay, sir. And sir, as means I am requesting to all the teachers, so I am doing it for you as well. That
Yes.
when the offline classes will start, means if it starts or not in this semester, I don't know. But sir, we all will request whenever the times permits or whenever the offline scenario comes, please means if you means show us the experiments in a
Yes,
offline
of
mode
course.
in a
Yes. That's what I said. I mean,
yeah, but
i-
if
i-
it means the semester also passes means down and we goes into the third year or in the fourth year, but we would
no,
then
no,
also love to
no, no,
have a
no. Don't be so pessimistic. Don't be so pessimistic. I mean, I don't know what will happen in this semester. I mean, because we were all set to start it from the start of this month, and then this thing came again. But yeah. But yes, please carry on. Hmm.
yes sir, that's what, because we all also thought that after third semester we'd get an offline classes means
Mhm.
but these online classes are out of our expectations actually.
Yes. No, you were saying something. I mean, you were after about the lab or something. I mean, you were.
Yes, sir. I was saying that means we would love to have the offline classes because we are
Sure.
lagging the means offline experience of every classes actually, be it a workshop class or a hand engineering drawing class. So means that's
Yes,
what I'm
sure, sure.
requesting to.
I mean that will definitely happen, but then there are I don't know. I mean, there are certain, I mean, things, certain things have to be worked out. Or, for example, normally what happens, your class is, I mean, previously before the this pandemic set in, what used to happen, there used to be two teachers for each lab class, and the class used to be class of this group of 25. They used to be divided into two groups of say around 10 to 12 students each, and the two experiments were simultaneously being carried out. Okay, so but now I mean, only one teacher has been assigned, is being assigned for the last few semesters. That is one reason being that this uh, they are being conducted online. So, I mean, even when it opens right now, immediately it may not be possible to carry on in the exactly same mode like all 25 students uh, I mean, crowding around one setup and seeing the things. So we have to work out maybe say if there is say six readings, maybe we have to break it up in groups of some four or five, three or four groups or something like that, so that one some I mean one group sees two sets and leaves, and then the next group comes. Something like that has to be worked out.
Yes, sir. Yes, sir.
Mm, okay. So today the experiment that we shall be doing is called determination of thermal conductivity of an insulating powder. Okay. So first I will explain the setup, and then I will explain the. I mean, first I will explain the theory. Can you see my screen?
Yes, sir. It's
Yes,
visible.
sir.
Okay, fine.
Yes, sir. Visible it is.
Mhm. So basically, for each experiment, there is a title of the experiment and there is an objective. I mean, you are familiar with this format from your electrical lab also, right?
Yes,
So
sir.
each experiment has a title and an objective. Not one objective, there can be multiple objectives also. So here the title is I mean, it should be the determination of thermal conductivity of an insulating powder. And the objective is to determine the thermal conductivity of an insulating powder. In this case, we are using asbestos powder. Okay. So basically, some unknown powder, if you are given with this setup, you should be able to find out its thermal conductivity. Okay. So here the background theory is like this. I mean, basically the powder is filled in a is used to fill up an uh, a spherical annular space like this between two spherical shells. There is an inner spherical shell and an outer spherical shell, and inside the inner spherical shell there is an electric heater. Okay. So can you tell me why we specifically go for an for a spherical geometry?
So maybe the boundary condition suits the calculation. So this was selected.
Boundary condition suits the calculation means in what way?
I mean, from calculation point of view, maybe the cylindrical geometry favors the calculation. It makes the calculation easier. So this was selected.
No,
Sir, I think it is. Sir, it is because of due to the heat transfer will take place due to the heat generation only. That will be the electric heater for the in the case of the spherical.
no. You can have a cylindrical or rectangular geometry also with heat generation.
Sir, but means I don't know, but will the edges will matter or something? Because
Right,
in a spherical
right,
geometry,
right, right. So what is happening is that when you are talking of so here, to simplify the theoretical calculation, we would like to go for a one-dimensional geometry. Okay, so only in a spherical geometry, if you can remove the angular angular variations, you can get an exact one-dimensional geometry. In case of a rectangular slab, it will be one-dimensional only if only if the two other dimensions, that is the length and the width, are infinitely large. There will be no heat transfer at all in those two directions. Heat transfer will be only across the thickness. So since that is not possible, so what does a one-dimensional rectangular geometry? I mean, in the context of rectangular geometry, what does a one-dimensional thing mean? It basically means you have a very large slab where the thickness is much less compared to the other dimensions, so that the major major heat flow is along the thickness. But this will be true in general, but it will be violated near the edges. So if you have to if you have to take a very large geometry, maybe, I mean, ideally, maybe something like a say, a carom board size of things. Say the plywood of the carom board. Say the length and width of the dimensions of the carom board, and the thickness is the thickness of the board. So something like that. Even then, near the end, we have some edge effects. Similarly, for if you go for a cylindrical geometry, then if there is no variation in the circumferential direction, so in that direction, in the theta direction, there will be no heat flow, but there will be I mean, the heat transfer will be restricted to only radial direction the if the length or height of the cylinder is infinitely large. So in real situations, what happens if you have a cylindrical geometry? You have to have a very long cylinder, but even then there will be some approximation. The one-dimensional approximations will break down near the ends. But in case of a spherical geometry, if you can ensure that there is no variation in the angular direction, so what are the three coordinates in case of a spherical geometry?
So R theta phi.
Are theta and phi. So if you can ensure that there is no variation in temperature in theta and phi directions, then identically, irrespective of the size of the sphere, identically it will always be the heat transfer will be only in the art direction only. And in fact, here you don't have to make the spherical shell very big or sphere very big. In fact, possibly if you make it small, it will be better, because if you make it big, then ensuring uniformity over the entire spherical surface over entire theta and phi directions, that may be more challenging. Okay, so that is the reason why we are going for a spherical geometry. And of course, if you are putting it inside a sphere, then the whole, I mean, you can enclose the entire heat flux within the surface. So, I mean, if you remember what you studied in radiation, I mean, this is something you studied in your radiation also. I mean, when you were talking of two-zone enclosure, so you studied two-zone enclosure, three-zone enclosure, those things in radiation.
yes, sir.
Yes, sir.
Yes. So when you studied there also, if you remember that two spheres, that was an exact representation of a two-zone enclosure. Two parallel plates or two coaxial cylinders, they were approximations. So for the same reason, okay. So here then what we are having a two spherical shells, and those shells are made of metals, so that there is, so even if there is some non-uniformity in the heating, because of the high thermal conductivity, the temperature non-uniformity will quickly smoothened out, so that so this is a metal surface and this is a metal surface, and the gap is filled up with the insulating powder. So by putting metal surfaces, we ensure that we have very very small temperature variations, okay, because the high thermal conductivity, even if there is some non-uniform heating, that the resultant heat flux uh, will not cause any significant temperature difference. You just wait, I'll be back in a minute.
Okay, sir. ए तुम लोगों ने कन्वेक्शन पढ़ा उसके बाद जो बलराम कुंडू ने पढ़ाया था?
হিট এক্সটেন্ডারটা দেখেছিলাম ভাই, আর ওটা দেখা
হিট এক্সচেঞ্জারটাও তো পড়ায়নি তো,
হিট
ওটা দেখা
এক্সচেঞ্জারটা তো ইয়ে থেকে পড়ে নিয়েছিলাম, আন একাডেমি থেকে।
না, ওটা
রেডিয়েশন তো
মনে
স্যার ঠিকঠাক করে
হয়
পড়ায়নি।
কি আন একাডেমিতে যেটা দিয়েছে সেটা মনে হয় 1 ঘন্টা 2 ঘন্টার ভিডিও, তাই না?
না, কে বলেছে?
দেখেছি ভাই।
আচ্ছা,
আন একাডেমির ওটা তোর কত ছিল, 8টা ভিডিও ছিল, 1.5 ঘন্টা করে।
স্যার এটা কবে ছিল? হিট এক্সচেঞ্জারে?
হ্যাঁ, হিট এক্সচেঞ্জার।
তাহলে দেখতে হবে। হিট
হ্যাঁ, বিটু স্যার বলেছিল তো টাইম থাকলে সবাই বলতে পুড়িয়ে দেবে। দেখ
আর দরকার নেই ফোন, ও নেটেই
ভাই
ভালো
ও
আছে।
হবে না, আর দেখে নিস, ও স্যার ব্যস্ত থাকবে, ও হবে না, ওটা আমাদের নিজেদেরই পড়তে হবে।
তো আন একাডেমিতেই ভালো আছে।
ওটা শুধু আর কি একটু একবার দেখতে হবে, মানে প্রত্যেকটা এক্সপেরিমেন্টে কোন থিওরি গুলো লাগছে সেগুলো আর কি আগে থেকে দেখে রাখতে হবে, তাহলে
হুম।
প্রবলেম হবে।
কনভেকশনটা বড় আছে এখানে, এই লাস্টের পার্ট গুলো
খুবই বড় আছে
কনভেকশনটা তো তোর
কি
অনেকটাই
হয়েছে?
বড়।
কি হয়েছে?
Sir, actually, in the previous semester we have heat transfer, but due to the time shortage, Balram Kundu sir couldn't complete, means even couldn't start the heat exchanger part, and he had
রিডিউস
just
দ্য হিট
introduced
কন্ডাকশন
the
পার্টটাও
heat
রিডিউস করে দিয়েছে।
convection part. Means he had just we have only 1 or 2 lectures on convection, and
And sir,
rest
also
like
radiation
80%
also
of
not
the
completed.
yes
Okay,
sir,
okay.
most of the heat transfer syllabus is not completed, so means we are trying it by ourselves.
Yeah. So you are trying it by yourself from where?
Sir, from
YouTube,
YouTube lectures or
আন
by
একাডেমি।
reading the book.
No. You go for the NPTEL lectures. I mean, there is one heat transfer course on NPTEL.
Yes, sir.
It's by although it is listed under chemical engineering head, but
Sir,
it is
sir Dashgupta.
Dashgupta. Yes.
Yes, sir. I have written the means the radiation part from there and the conduction a little bit. But I have not completed the convection till now.
Yes,
Means
you follow that. I mean, because that is a very good lecture. I mean, there are two lectures in two NPTEL courses on this basic heat transfer. What you studied, when both are from chemical engineering. One is from IIT Bombay and one is from IIT Kharagpur, Professor Shunanda Dashgupta. But Professor Dashgupta's lecture is more tuned in the way we study in mechanical engineering. The other one with probably Professor Ganeshan or somebody. I mean, from IIT
Guy
Bombay.
Tonde, I think, from
Huh?
IIT. Guy Tonde, the
No,
professor.
no, no, no. Professor Gaitonde's lecture is there. I didn't see that. Professor
Yes,
Gaitonde
sir.
is, of course, from mechanical engineering.
Yes, sir. It's from mechanical. I think it's from 2008. The lecture is presenting.
Is it a video lecture or a web lecture? Web
So
based.
it's so it was a video lecture, sir.
Okay.
There were like the NPTEL videos of all the subject. There was a lecture of heat transfer from IIT Bombay. It was taken by Gaitonde sir
Yeah,
and
Gaitonde, Professor Gaitonde, yes, Professor Gaitonde is of course from mechanical engineering, a very senior person. Probably he has just retired or something like that. I mean, yeah, yes, you can go there, but I have not checked that lecture. But right now, what are the courses that are being actually offered now in their certificate courses? The two are, one is this Professor Dashgupta's course, and another is also from IIT Bombay, but that is a that is also from chemical engineer. But Professor Dashgupta's course is more tuned to the way you have learned in the class. So, the other one from IIT Bombay, not Professor Gaitonde's one. I have not seen that. So it is more tuned to the way chemical engineers learn it, with more emphasis on process heat transfer. So you can go through Professor Dashgupta's lecture. In fact, Professor Dashgupta is an alumnus of our chemical engineering department, and he maintains a very close contact with the uh, with his department. I mean, with all the departmental alumni activities and other things, he comes and everything.
oh, that was not known to us actually,
Yeah,
means not me.
yes, he is a graduate of 1985 batch, chemical engineering. Okay, uh, so
Sir, Bratish wants to join. Could you allow him?
British, he
So
was
he
there.
was present, I think.
So that means, yes, sure,
Oh, sir, he
he
joined.
has joined.
Yes, sir.
Normally, it should not affect. I mean, if someone tries to rejoin, it does not affect. I mean, if someone,
So sir, basically I used the wrong link.
okay,
Sir, I completed from Unacademy, so it may be affected. Means, sir, NPTEL lectures are, I feel quite boring. The professors are
boring.
very, স্যার হ্যাঁ মানে অনেক মানে লেন্দি ভিডিও থাকে কিন্তু মানে আনএকাডেমি স্যারগুলো বেশ এনার্জি নিয়ে পড়ে ওটাই আমার বেশ ভালো লাগে এটা
Sir, actually, he want means very compressed lectures. Means his preference is like that.
Uh, compressed
So
lecture.
there is
স্যার নট
so
লাইক
there is another heat transfer lecture.
Okay. We will discuss about. I mean, we will discuss about it after I finish this thing. I mean,
Yes, sir, yes,
I
sir, sure.
have some. Uh, I mean, why I suggested NPTL, I will tell you. Okay. Okay. So here what we do. So here basically we have an electrical heater inside, and there are two metallic shells. Metallic shells ensure that there is a very negligible temperature. I mean, circumferential temperature variation, circumferential and azimuthal, polar and azimuthal temperature variation, and and the electrical heater. If you know the power input to the heater, then then under steady state condition, the rate of heat transfer would be equal to rate of heat transfer to the device would be equal to the rather rate of heat transfer from the device, that has to be equal to the rate of heat input to the electrical heater. So if you know how much heat is being input to it, so you know how much heat is being lost, and then that will give you this q dot. And then if you know the temperature of the inner shell and the temperature of the outer shell, and you know the inner and outer radii, then you can calculate uh, calculate that the
Yeah.
your only unknown becomes this thermal conductivity, and you can calculate it. So that is the underlying theory. So actually it's a very simple theory. So this is how the setup actually looks like. So this is the sphere, the spherical shell in which the asbestos powder is housed, and there are actually 10 thermocouples, six on the surface, sorry, 6 on the outer surface, on the outer shell, and 4 on the inner shells. I mean, these are the thermocouple leads. Uh, and this one is the control panel where you get all the readings. So basically this is the main switch where you through which you start the power supply. This is the heater control, so this controls the heater power. So basically it looks like this. These are supposed to be the power inputs, that is, these are supposed to be in watts, but you do not directly use it in calculation. You just use it as a as a set point. So for example, if you want to set a get a voltage input of, say, of certain value, you should always take the take the pointer to a particular reading on the dial. So basically this allows you to set the power, and this and also to allow repetition of the results. So it is something like you're turning your gas knob, in the knob in your gas oven. I mean, those say 1 2 seam high, I mean those things, they really do not give you any quantitative information, but they give you some qualitative idea that when you go from 1 to 2, you are basically increasing the fuel supply, something like that. So similarly here also, when you are setting the power to 20 watt, then it is not exactly, you are not using that to be the power input to be 20 watt, but correspondingly whatever will be the voltage there will be a voltmeter reading here, and whatever and the corresponding current in this ammeter reading, these values are ones which you are using in your calculations. Do you understand this? I mean, so you are not although we are controlling it, this is a control unit, we are controlling it with the help of this dial, but we are not using these readings directly in our calculations. And then there is a temperature indicator here. So this temperature indicator will give you values for all the 10 temperatures. I mean, these 10 thermocouples, readings from all the 10 thermocouples will be displayed here. So how do you know which thermocouple reading you are getting? For that there is a temperature selector switch. So by choosing, so this 1 to 10, 1 to 12, there is a provision for measuring temperatures from 12 different positions. So here we are actually using only 10 positions, so 2 positions are left open. So starting from 1 to 10, if you just turn the selector switch to one of these values, and then the reading that you will get in the indicator will correspond to the first thermocouple or second thermocouple or fifth thermocouple or ninth thermocouple, this way. So the first 4 are for the inner shell, and the last 6 are for the outer shell. Okay, so is the setup clear?
Yes, sir.
Yes, sir.
Sir, but one thing,
Yes.
sir, the inner sphere will be there inside that sphere. Sir, how it is placed, means is there some stand something, or we just put the whole insulation and keep in an approximation inside the outer shell, means how is the inner shell placed inside it?
Actually, there is some support, so that way it disturbs the the spherical symmetry to some extent. For example, even here you can see that you have to have this ring like support
Yes,
to
sir.
hold it. So strictly speaking, this also provides a heat transfer path. So
Yeah.
that way there is a disturbance. I mean, if it had to be completely spherical, then it should have been just levitating in the in air. So that is not possible. So similarly, in the inner shell also has some support structure to place it inside, and when designing, you have to when designing and manufacturing, it has to be taken care of that there is zero or minimal eccentricity.
Okay, sir.
Okay, so these are the specifications. So diameter of the inner sphere is 10 centimeter, outer sphere is 20 centimeter, and inside it there is a mica heater. Similar to mica heater means nichrome wires on a mica heater, which is nichrome wire. So it is similar to what we have in electric iron. So we have these nichrome wires sandwiched between mica sheets. Uh, we use mica sheet because mica is one of those rare materials which has a very high thermal conductivity but very low electrical conductivity. So there is no risk of short circuiting. Yet there is very easy passage of heat. So that's why we use a mica heater, and then this temperature control unit. This is this heater control unit. This one is called the dimmerstat. Dimmerstat means basically it is similar. It is some kind of a rheostat kind of thing. So where you control the power, it is graduated in power. You control the power input to the system. Okay, and then the as insulating powder is asbestos, and the digital temperature indicator, in each of these cases it is ranged from 0 to 300 degrees Celsius, but actually we will go for much lower levels of temperature, and there is a digital voltmeter and a digital ammeter. So these are the appliances here, and their specifications. Okay, so what is the procedure? First we have to put on the main switch, that is this main switch. First, you have to put on this main switch. Then we have to apply input power by operating the dimmerstat. But the precaution is that one should not exceed 40 watt to prevent burnout. So if you look at the scale, so you can see that it gives, you can go only up to only over a very small range of the scale. Okay, so 0 to 40, you should not exceed this value to prevent overheating. Then you wait until a steady condition is reached. So how do you know a steady condition is reached? You say you go for a particular position of the of the select temperature selector switch. That means you keep the reading for one particular value, one particular position, and you see that nothing is changing. So you repeat this for once one of the readings have become steady, you repeat it for all the other values and allow some time, and you see that nothing is, it's not changing with time. So then you know it has reached the steady state. And the attainment of steady state is important, so that you can say that whatever power is supplied through the electrical heater will be transferred to the ambient by heat transfer. Otherwise, till the steady state is reached, there will be a gradual increase of temperature of the setup, which means there will be some amount of energy will be stored in the setup. So the heat transfer to the ambient is less than the amount of energy that is being supplied, or at least it will be different from what is being supplied. Okay. So once the steady state is reached, you note down the readings in the observation table. Basically, here the readings will be the readings of the 10 thermocouples at the 10 different positions. So after this is done, you repeat the experiment for a different heat input.
Sir,
That-
sir, can you repeat the steady state reach condition you say?
Yes. So how will you understand that the steady state has been reached? So you put the temperature selector switch to one particular position, and that will give you the temperature indicator here, and you just leave it at that position. So initially you will see that initially there will be a very fast change in temperature, I mean in the temperature indicator reading. Then gradually the changes will become slow, and finally there will be no change at all. I mean, you will see that the temperature remains practically constant. So that means this, then you can, for a sufficient length of time, for a reasonable length of time, and then you can say that it has reached a steady state value. This particular, at that part, this particular location, a steady state has been reached. So you change the selector switch to a different position, and again allow some time and see that nothing is changing. So when all such positions show you no such changes, that means you understand that a steady state has been reached, and there are no changes in temperature with respect to time. So in that case you can say that there is no more heat storage in the no more energy is being stored in the system. Whatever is entering the system is also leaving the system. So we know what is entering the system. So once steady state is reached, we know how much is heat is leaving the system, or how much heat is being transferred across the asbestos powder layer. Okay.
Yes, understood.
So you repeat the experiments for different heat inputs, and then after the experiment is over, first you put the thermostat to 0 position, and then you put off the main switch. Okay, so these are the observation tables. So these are what you have to note down. So this is the serial first the different serial numbers, they correspond to different heater powers. So for the first for each set you have to you have to take the readings of the voltage and the current from the digital voltmeter and digital ammeter, and then the 10 temperature values, the 6 on the inner shell here, different points, and 4 on the outer shell. Okay. So basically,
Sir, you 4 on the inner shell and 6 on the outer shell, I think.
yes.
Yeah.
Oh, did I say the opposite thing? Okay.
Yes, sir.
Oh,
Actually, the
good.
PPT
Oh,
also
okay, yes. This will be outer. Thanks. So, I will show you the actual picture. So this is how the thing actually looks like. These are some of the sketches that are provided by the manufacturer. Okay. So basically, this is how the chair is there. So this support thing, it is not very clearly shown, but basically the thermocouple readings are shown here, and the thermocouple positions are shown here. This is again a schematic diagram. So here we are assuming that these locations are very close, so that when you are talking of the diameter of the sphere, basically we are taking them to be at the outer location, and these 4 to be at the inner location, and this is the heater. So basically it is like a disc kind of thing at the placed on the diametral plane. Okay. And So
Sir,
this is
the diagram you showed, it was the section view, right?
diagram was a section view, right? It was a section view, but even then it was more of a schematic diagram. I mean, just not a very you know, not a very proper engineering or manufacturing
Yeah,
drawing.
I can understand. Sir, that means the outer means the six readings will be means approximately equal to each other.
It should be, yes.
Yeah.
Because that will happen because uh, of two things. One is that there is the heating is more or less symmetrical, although it will not be
Yeah.
exactly symmetrical. You can understand
Yes, sir. Yes, sir.
because you can understand that it will not be exactly symmetrical because the heater is like this. So these points they should be closer to the heater corresponding than these points. I mean, if the heater itself was another spherical shell, then it would have been perfectly symmetrical, but
Yes,
that
sir.
is
Yes.
very difficult to achieve. But that is not a big problem because we are using metallic shells. So whatever, even if there is some small difference in heat flux here and there is a net flow of heat along the circumferential direction, even then, because of the high thermal conductivity, that heat flow will be sustained with a negligible temperature difference. So we can assume the temperature of the surface to be isothermal. I mean, to be constant. The inner surface to be at one temperature and the outer surface to be at another temperature.
Okay, sir.
Okay, so then if we come to the calculations, so basically this is the calculation you will be doing. First, you have to calculate the average temperature of the four inner thermocouple readings, assuming that they are not exactly same. So this will be this T1 to T4. This will be experimental observations, and you do this calculation. Similarly, T5 to T6. I mean, everything that is given in red circles are experimental observations. Whatever is given in is blue circle, that is given geometrical things, and whatever is given in green is calculated. So here you calculate the average inner surface temperature, average outer surface temperature, and heat input. And then you use those calculated values along with the given radii in this formula to get the thermal conductivity. So this gives you the thermal conductivity for one condition. So in the next, when you go for the second, so this will be your result table should look like this. This will be your uh, these are the calculations that you are getting. So because you are doing the calculations for different power inputs, so the temperature levels will be different. So so the thermal conductivity they will not be exactly same because thermal conductivity itself is a function of temperature. So you should be getting some variations. Okay.
Yes, sir.
So once you do that, then from the different readings you get thermal conductivity for different inner inner surface temperatures. So you plot the thermal conductivity as a function of Ti. So that's what that completes your job. Okay.
Okay, sir. So, but we have only two K readings for TI. So means
No. You will not have two. I have just shown it here as two. Probably we'll have.
okay, okay,
I mean, normally in the experiment we do some three or four sets of experiments.
okay,
Okay.
sir. Okay, sir.
Sir,
Sir, here, sir,
Hmm.
sir, here we have not taken the thickness of the inner sphere. That must also have the thermal conductivity.
আগে বলো।
তো বলছি ইনার স্ফিয়ারের থিকনেসটা তো আমরা মানে নেই, ওটা কি নেগলিজেবল ধরে দেওয়া হয়েছে? মানে ইনার স্ফিয়ারটারও তো থার্মাল কন্ডাক্টিভিটি আছে, ওটা তো
হ্যাঁ
আমরা
হ্যাঁ
Yeah,
হ্যাঁ
yeah, yeah.
আছে কিন্তু আমরা যদি if we put the inner the T1 this 1 to 4 those thermocouples if they are put near the outer surface of the inner sphere and T5 to T10 they are put near the inner surface of the outer sphere, তাহলে মানে
হ্যাঁ স্যার।
তাহলে ওই এটা থাকবে না। আর যদি থাকেও তাহলে যেটা হবে, বিকজ অফ দ্য ভেরি হাই থার্মাল কন্ডাক্টিভিটি, তোমার দ্য থার্মাল রেজিস্ট্যান্স উইল বি ভেরি লো।
Very negligible.
মানে এইটাই যদি তোমার মেটাল, হ্যাড দিস নট বিন আ মেটাল wall, but say something like a plastic wall, or a bakelite wall or something like that, then with the same thickness, that might have contributed more.
Yes sir.
Okay. And so the other thing is that what you have to do in your report, the layout of the report. Actually, in the heat power lab, we insist on mini reports being very very thin. I mean, we don't want you to spend too much time writing the reports. Rather, we like you to study that thing. So what you have to do first, there should be a cover sheet. I mean, normally those cover sheets are available. There are some cover sheets available in the in the student chip stores. I mean, next to the FETSU office. But now you cannot get it, so you will make a cover sheet for yourself, which should contain these information: name, class, section, and full roll number. That is the full 12-digit roll number. Then the title of the experiment as given in the lab sheet. I will show you the. I will share with you the lab sheet.
Sir, will you be sharing this Word file or means
Yes,
and the PPT?
yes, everything.
Okay, sir. Okay, sir. Okay, sir.
And then the title of the experiment as given in the lab sheet. So that's why, because it is given in the title as thermal conductivity of insulating powder, I also mentioned it like that. I mean, although ideally it should have been determination of thermal conductivity of insulating powder. Uh, then the objectives of the experiment, as I mentioned in the first slide, and that is also given in the lab sheet. Then the printed lab sheet, which I will share with you. I mean, normally in physical class, you would be giving one copy each of the physical lab sheet, and that at the end of the class you have to get signed by the class teacher. So, which in a way is a proof of your attendance. But so without this lab sheet, it's generally not accepted. But here also you just put it in. Then there will be the printed diagrams that I showed you. That also I will share. You just include it in your report. Then the observation tables, you make an observation table. You can do it by hand. I mean, it need not be whole thing be typewritten. I mean, it should not be typewritten. Rather, you do it by hand. The observation tables, same format as in the lab sheet. All the If you are doing it for 4 different power levels, the observation table should contain all the details. But then there should be a sample calculation for one run. You do all the detailed calculation, all the calculation steps. That is called sample calculation. You do that,
Okay,
and
sir.
then you draw the graphs. For this, you can use Excel or graph paper, whatever is you are comfortable with. Okay.
Okay, sir.
That's all. That should only these things should be in the report. I mean, you need not describe any procedure or precaution or causes of error. I mean, those are the things you should know. They can be asked in the Viva, but not, you don't have to include it in the report. Okay.
Okay, sir.
So let me take a let me stop the recording for a while,
Yes, sir.
just to keep the size of the recording